All right, so in the original lab activity, okay? In the original lab activity, we graphed two things. We graphed the pullback distance, measured in meters, and the speed, measured in meters per second. Now, so we had like 0, 0, this was 0.03, this was 0. Was it 3.9? Was it 3.9? Did someone check their days at 3.9? Okay. And then, so we got a nice linear relationship. I felt really good about that. This is the pullback distance. This is the speed. Okay. A nice linear relationship was good. Now, what I wanted to know, because we're really studying energy, how did the energies associated with these relate? So, we had, in this column, we were trying to figure out the elastic energy, and in this, we're trying to figure out the kinetic energy. Now, how do you calculate elastic energy? Well, 1/2 little k x squared, where x is, in this case, is the pullback distance. And I told you for our rubber bands, little k was equal to 120 newtons per meter. So, if you go to plug and chug this, it would look like this. I want to figure out the elastic energy. I'm going to take 1/2 of my k value is 120. And then what was my x value? It was 0.03. Don't forget to square it. Okay? And then so you put this in a little calculator, and someone, who got a number for me here? What's that number? I know many of you did it on Friday. What is it? What's that mine? So, okay. Now, what about the other column? What about the kinetic energy? Well, 1/2 mv squared, where the speed, this is the speed v, so you're going to get it out of there. And I told you the mass of the car was 0.5 kilograms. And so if you want to calculate the kinetic energy, there we go. Now, that's how to plug and chug the data points. Cool. And then the next row would be 0.06, and I think it was 0.75 or something like that. And you just plug and plug and plug, and then you get this, and you graph this, and we're going to see what happens over here. Now, what's cool about this, okay? So this is the elastic energy you put in, and this is the kinetic energy you put out. Here's the thing. For this first data point, this is what I'm interested in. How much elastic energy did you put into the cart in the spring? 0.054, correct? And then how much did you measure later on? 0.035. You put in 0.54 and you got out 0.35. You with me on that? where is the rest? Okay? Check your neighbor now. Maybe your neighbor knows. Where is the rest of the energy? Check your neighbor now. See if your neighbor knows where the energy went. Okay? Check your neighbor now. Does that make more sense? Where do you think it went?
I don't have a clue.
Really? When we look at the pie charts, for example, okay, when we look at the pie charts, if you have all elastic energy here, okay, what's our energy situation over here? Is it all kinetic? It's not all kinetic. It's a lot of kinetic, right? But what is some of it? That's right. And in this case, we know exactly how much. So what I like about this is we know the size of this pie is 0.054, correct? And then how much thermal, or how much kinetic energy is there? 0.035. And then so how much thermal energy does there have to be then? 0.019. See how that works? Because we know the total amount was 0.054, and then so if you take 19 plus 35, you probably get 54. See how that works there? So we expect this to be a little bit, we expect the kinetic energy to be a little less because of the fact that there's some thermal energy. In this case, we have a good representation of it. Is that cool? So your goal, finish this column, plot this, finish the lab. All right? Let's take about 5 or 6 minutes, see if you guys can finish this up. All right? Do that right meow. Okay? You're probably going to need to get one. You finished up, Randy?
Yeah.
Perfect. What was your slope? 0.6? Perfect. Yes. You want to charge it? Oh, sure, you can. Those computers are available. You can go sit there. Either way, it's fine with me. Yep. Graded over the weekend. Played with my children instead. Gentlemen and ladies, keep your phones in your pockets, please. I understand that you're done, and that's excellent. I'm excited about that, but the current rules are Gotta get ready for today's activity. Dun, 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 dun. Oh. Didn't seem safe. Everybody good? We all done? No, we're working on it?
Make some calculations.
Good. Color comment. Good. Your slope was, you said, what, 0.59, 0.6, something like that? Yeah. Awesome. Okay, finish those. All right, everybody done? Close to done? Kind of close to done? Maybe close to done? You're done. Won't be done. How's it coming? Almost there? How's it going? Why is it so dark? I can't see it. Ooh. You have the data from the other day? Why? The data from last week's classes.
What day?
Wednesday, Thursday, and Friday. All right. You guys ready? So let's set aside that for now. You can finish it up. You can finish it up later. So you can close your computers for now. And what I want to do is, whatever you're drawing on, get out that now because I want to start drawing a little bit. And I want to get us ready to analyze the next set of data. Okay? I want to get us ready to analyze the next set of data. Now, I know this is backward compared to what I drew on the board, but we'll just have to use our imaginations. So what I'm going to do is I'm going to take my cart here. Okay? I'm going to take my cart and I'm going to pull it back like this against the spring. So I'm going to take my cart, I'm going to pull it back against the spring like this. I'm going to let it go. Goes up the ramp. Is that cool? Now, here's the deal. I'm going to pull it like this. It's going to go up the ramp, it's going to stop, and it's going to come back down. I'm interested in the moment that you let it go here, and then the moment that it comes to a stop up here. So we'll use pie charts. What do the pie charts look like? Okay? What do the pie charts look like the instant that you let it go and the instant that it's at the highest point? Okay? What do the pie charts look like? So go ahead and draw some pie charts now. See if you and your neighbor can figure out what the pie charts look like. Pie charts are like, let's see what you got. So at the top of its path, it stopped here momentarily, right? It stopped for an instant. So when it's on the way up, obviously there's kinetic energy, but when it gets to the very top, it stopped there, right? So there's not going to be any kinetic energy at the top. Make some pie, please. Make the pie, make the pie, make the pie, make the pie. Make the pie, make the pie, make the pie. All right, what's in the first pie? What's this one, Peter? Well, it's not moving yet. This is
not moving yet.
just when you let it go.
It's elastic.
All elastic?
Yeah.
I agree. Okay. Preston, what about this one?
I said nothing, but then it stopped.
So there's no kinetic because it stopped. Go ahead.
Gravitational thermal.
Yeah, so as it rolls up the hill, has it changed its height? It has, right? And if you change your height, you're storing energy in the gravitational field. So there's some amount of gravitational energy, probably a large amount, and maybe some thermal energy also, because it was a real thing rolling. Yeah, if you go up a hill, the energy has to go somewhere. Has to go somewhere. How's that? Is that cool? And today what we're going to do is we're going to explore this relationship and see if we can't figure out exactly what's happening here. Is that cool? Yeah.
I have a question. Are we gonna do pie charts or are we gonna do the bar graphs?
So pie charts and bar charts are both useful, okay? And we're going to want you to be able to do both of them. So for example, okay? For example, for this one, so for this one, we know we're starting with some amount of elastic energy. Okay? And you can represent it as how many ever boxes you want. And then in our system, we have things like the spring, the cart, the G field. And then so according to this, we're going to gain some amount of gravitational energy. And we're losing some to thermal energy. So the energy went from the spring into the cart, and then from the cart, it went into the gravitational field, and some left the system completely and went into thermal. So I want you guys to be able to do both. And today we're going to see if we can't quantify it. Okay? But what are we going to explore today is the question. So what is one of the things that you determine when you're doing the lab? Or I'm determining it because I'm doing the lab. What is one of the things that you determine? What am I deciding when I do this? What do you think?